Pluto, a former planet that was downsized to a dwarf planet, remains a subject of interest and focus in the cosmic community. As demonstrated by recent findings by leading scientists, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising concerns about a potentially perilous impact between these two planets, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full revolution yet. The intrigue doesn't stop there. Pluto's orbit is marked by its notably elongated shape, straying far from the near-circular orbits of the major planets. What makes Pluto's orbit even more curious is its tilt, set at 17 degrees to the ecliptic plane. The way Pluto follows its orbit is significantly more extreme compared to the other planets. This inclination and eccentricity add layers of complexity to its orbital path. One of the most fascinating aspects of Pluto's orbit is its intersection point with Neptune's orbit. For nearly 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, defying what we might expect based on their positions in the solar system. This raises the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to decipher its peculiar path. Unlike other planets whose orbits lie mostly near the ecliptic plane, Pluto's orbit juts out with its steep inclination and elongated shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit, despite these complexities, is evidence of the intricate mechanics of space. The three-body problem in space involves figuring out how three objects like Pluto, Neptune, and the Sun move and interact with one another due to their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem reveals how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex manner. The terms alpha libration and degree libration, along with the VZK oscillation, are crucial to solving this puzzle. As explained by astrophysicists, what keeps all planets in their orbits is a phenomenon called alpha libration. For Pluto and Neptune, this means that whenever Pluto crosses Neptune's orbit, it is at least 90 degrees away from Neptune. This spatial separation is critical in preventing their orbits from crossing. Degree libration, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is situated well above their orbital plane, providing an additional layer of protection from potential collisions. Another significant factor is the VZK oscillation, named after three scientists, von Zeipel, Kozai, and Lidov, who studied how objects move in space. It explains how three celestial bodies like Pluto, Neptune, and the Sun gravitationally influence each other. For Pluto, the VZK oscillation accounts for why its orbit around the Sun is so unusual. Despite its seemingly erratic path, this oscillation helps keep Pluto moving smoothly for billions of years. The VZK oscillation demonstrates that, although things in space may appear chaotic and random, certain patterns and forces maintain order. These factors help stabilize Pluto's orbit, ensuring it doesn't collide with Neptune or drift away. This three-body problem is essential for understanding how orbits evolve due to gravitational interactions. Studying this helps us learn more about Pluto, our solar system, and distant stars and planets. Numerical simulations in the late 1980s revealed that, despite these stabilizing properties, Pluto's orbit is inherently chaotic, with slight deviations in initial conditions leading to significant changes over time. However, these unusual properties of Pluto's orbit have been found to maintain overall stability over very long time scales, keeping the chaos in check. Recent computer models have further helped us understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune has a unique relationship with Pluto, where, for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance stabilizes Pluto's orbit. But Neptune isn't the only factor. Jupiter's gravity also plays a massive role in safeguarding Pluto's orbit, and Saturn contributes as well. These studies show that Jupiter's gravity alone is strong enough to ensure Pluto remains on a stable path for extended periods, potentially even billions of years. It's as though Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely in space without causing any problems. These peculiarities are crucial in the broader context of the universe, maintaining order and stability in the movement of celestial bodies. Without these elements, the solar system as we know it would be a much more chaotic place, with bodies like Pluto potentially colliding with others or being flung out of their stable orbits, leading to a cascading effect on other celestial objects. This is particularly important when considering Pluto's potential interactions with Neptune in the future. Pluto's unique orbit highlights the delicate balance of forces that governs our solar system. Despite its small size and reclassification as a dwarf planet, Pluto provides astronomers and astrophysicists with valuable insights into orbital mechanics, celestial stability, and the dynamic interactions between planets and other bodies. The resonance between Neptune and Pluto, known as a 2:3 mean motion resonance, ensures that their orbits never intersect, despite their apparent crossing points. This resonance is a perfect example of how gravitational relationships between celestial bodies can create stability. Every time Pluto is at the point in its orbit where it comes closest to Neptune, Neptune is in a completely different part of its orbit. This synchrony prevents any close encounters that could destabilize their paths. Furthermore, the eccentricity and inclination of Pluto's orbit add layers of complexity to its behavior. When Pluto is nearest to Neptune, its orbital plane is well above or below Neptune's. This vertical separation, combined with the gravitational influences of the other giant planets, adds an additional safety mechanism, ensuring their paths remain distinct. Astrophysicists also point out that studying the chaotic yet stable nature of Pluto's orbit sheds light on similar processes occurring in other planetary systems across the universe. The three-body problem, which governs the interactions between Pluto, Neptune, and the Sun, is not unique to our solar system. Understanding how such systems stabilize over billions of years can help scientists predict the behavior of exoplanets in distant star systems. Pluto's orbit also challenges long-held assumptions about planetary motion. Unlike the nearly circular orbits of the major planets, Pluto's elongated path raises questions about the early history of the solar system. How did such an unusual orbit form? Some researchers believe that Pluto was once part of the Kuiper Belt, a region of icy bodies beyond Neptune, and that its current orbit is the result of gravitational interactions during the early formation of the solar system. Another area of interest is Pluto's interaction with its largest moon, Charon. The two are locked in a mutual gravitational embrace, with both bodies showing the same face to each other as they orbit. This unique relationship, known as tidal locking, influences the dynamics of Pluto's orbit and provides a fascinating case study for scientists studying binary systems. Looking ahead, the study of Pluto and its orbit continues to be a priority for astronomers. Modern telescopes and space missions like NASA's New Horizons, which provided unprecedented close-up images of Pluto in 2015, have expanded our understanding of this distant world. These observations revealed not only the intricacies of Pluto's orbit but also its geological and atmospheric complexities, such as nitrogen glaciers, towering ice mountains, and a thin, hazy atmosphere. In conclusion, Pluto serves as a reminder of the complexity and beauty of our solar system. Its orbit, shaped by gravitational interactions, chaotic dynamics, and ancient cosmic events, is a testament to the intricate balance that governs celestial mechanics. As scientists continue to study Pluto and its interactions with Neptune and other planets, we gain deeper insights into the forces that maintain order in our ever-changing universe. Whether as a planet or a dwarf planet, Pluto remains an enduring symbol of curiosity and discovery in the cosmic landscape. Understanding its orbit is essential. This gives us a clearer image of the nearby planet group's dynamic nature. The situation of Pluto demonstrates that even the most apparently unstable orbits can reach a state of equilibrium through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of continued observation and investigation of these phenomena to better understand our place in the universe. Exploring the depths of space often leads us to confront the peculiar nature of celestial bodies, and Pluto's orbit is a perfect example of this peculiarity. The concept of orbital chaos, which refers to the delicate dependence of a body's path on its initial conditions, is clearly illustrated in Pluto's case. This means that even slight changes in Pluto's position or velocity can significantly alter its long-term trajectory. Within the vast region of our solar system, Pluto occupies a unique position that challenges our understanding of planetary classification and dynamics. Since its discovery in 1930, Pluto has undergone extensive study, leading to significant discoveries about its composition and behavior. One of the most fascinating aspects of Pluto is its surface, which is a complex tapestry of ice, rock, and various compounds. The New Horizons mission, which flew by Pluto in July 2015, provided incredible data about this distant world. Pluto's surface is characterized by vast plains, towering mountains, and deep valleys. One of the most striking features is Sputnik Planitia, a large heart-shaped plain primarily composed of nitrogen ice. This region exhibits a diverse array of geological features, including massive ice blocks and what appear to be flowing glaciers. The presence of these features suggests that Pluto may still be geologically active, despite its great distance from the Sun and its low temperatures. Another intriguing aspect of Pluto is its atmosphere, which is primarily composed of nitrogen, with traces of methane and carbon monoxide. Pluto's atmosphere is thin yet displays interesting seasonal variations. As Pluto moves closer to the Sun in its elongated orbit, its atmosphere can expand and become more dynamic. This behavior reflects the intricate relationship between Pluto and its atmosphere. During Pluto's closest approach to the Sun, some atmospheric gases may freeze onto the surface, while as it moves farther away, these gases can sublimate back into the atmosphere. The relationship between Pluto and its largest moon, Charon, also adds complexity to the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that the two bodies orbit a point in space between them, rather than Pluto simply orbiting Charon. This unique relationship contributes to the gravitational dynamics of the region, affecting the orbits of other objects in the Kuiper Belt. The Kuiper Belt, a region beyond Neptune populated by small icy bodies, is home to many other dwarf planets and potential impactors. This belt is a reservoir of ancient material from the early solar system, offering scientists a glimpse into its development. Pluto's orbital characteristics may provide insights into the formation patterns of these distant objects, suggesting that interactions with larger planets may have played a critical role in shaping their current orbits. One of the key implications of understanding Pluto's orbital dynamics is its potential impact on our understanding of the solar system's evolution. Gravitational influences from nearby giant planets like Jupiter and Neptune can alter the trajectories of smaller bodies, including those in the Kuiper Belt. Such interactions can lead to changes in orbits, potentially causing collisions or ejections from the solar system. As researchers continue to study these interactions, they may uncover broader patterns that govern the behavior of celestial bodies across the universe. The exploration of Pluto also raises philosophical questions about order in cosmology. The decision to reclassify Pluto as a dwarf planet in 2006 sparked debates about what defines a planet. The International Astronomical Union's definition focused on criteria such as orbital stability and size, leaving many to ponder the implications of such classifications. This ongoing discussion reflects our evolving understanding of the universe and underscores the need for a flexible approach to categorizing celestial bodies. Furthermore, the potential for future exploration of Pluto and the Kuiper Belt remains an exciting frontier. With advances in technology and mission planning, scientists are considering sending additional spacecraft to study Pluto and other objects with similar orbital characteristics. Such missions could provide valuable information about the primordial materials that shaped our solar system, potentially shedding light on the origins of life on Earth. The role of exoplanets, planets beyond our solar system, is another captivating area of study that intersects with our understanding of Pluto. As astronomers discover an increasing number of exoplanets, particularly those in the habitable zones of their stars, the lessons learned from studying our own solar system may help develop theories about planetary formation and habitability. Finally, public interest in Pluto has remained strong, fueled by its enigmatic status and the stunning images returned by the New Horizons mission. The dwarf planet has captured the imagination of people worldwide, inspiring a renewed appreciation for the vastness of space and our place within it. As we continue to unravel the mysteries of Pluto and the celestial bodies that share its corner of the universe, we are reminded of the spectacular wonders the cosmos has to offer. Does Pluto's remarkable nature extend beyond its physical properties and orbit? It also serves as a crucial case study for understanding planetary development and the dynamics of celestial bodies. Pluto's formation is believed to have occurred in the early solar system alongside other Kuiper Belt objects. Studying its composition can provide insights into the conditions that prevailed during the formative stages of the solar system, potentially shedding light on the formation of terrestrial planets. Recent research suggests that Pluto may have a subsurface ocean, a discovery that could reshape our understanding of its geology and potential to support life. New Horizons data revealed that some regions of Pluto's surface, such as the icy mountains, may be composed of water ice, which behaves differently from typical rock at low temperatures. This discovery invites further exploration into the possibility of liquid water existing beneath its frozen crust, raising fascinating questions about the potential for life even in such extreme conditions. Furthermore, Pluto's relationship with its atmosphere can offer insights into atmospheric science. The seasonal changes in its thin atmosphere provide a natural laboratory for studying atmospheric cycles on a planetary scale. Researchers are particularly interested in how the interaction between solar radiation and the surface can lead to complex weather patterns, much like those observed on larger planets.